We'll practice calculate an impulse and average force in a collision and see how a crumple zone reduces force. Here's the problem. A 1,000 kilogram car traveling at 20 meters per second is brought to rest in a collision. Part A, find the impulse required to stop it. Part B, compare the average force if the car stops in 0.10 seconds, a rigid frame, versus 0.80 seconds with a crumple zone, and assess the safety impact. First, recall that impulse equals the change in momentum, which is mass times change in velocity. The mass is 1,000 kilograms, the change in velocity is 20 minus 0, so the impulse is 2.0 times 10 to the 4th kilogram meters per second. Now find the average force for the rigid frame. Force equals impulse divided by time, with delta t equals 0.10 seconds. 2.0 times 10 to the 4th divided by 0.10 gives 2.0 times 10 to the 5th newtons. Now with the crumple zone, delta t is 0.80 seconds. 2.0 times 10 to the 4th divided by 0.80 gives 2.5 times 10 to the 4th newtons. Extending the stopping time by 8 times reduces the peak force by 8 times, from 200 kilonewtons to 25 kilonewtons, greatly lowering the risk of injury. The key takeaway: increasing the time over which momentum changes reduces the average force, which is why crumple zones improve safety.